Assume a polymer contains 4 monomer units, n equals 4, and calculate the partition function using the zipper model. So here you have the values for Q is 1, S is 1.5, and sigma is 0.1. We will use this equation here in red to solve this problem. So first what we need to do is plug in the values to find the partition function. So Q is equal to 1 plus sigma multiplied by 4s1 plus 3s squared plus 2s cubed plus s to the 4. Basically, you solve this sigma problem with k from 1 to 4, which is the number of monomer units, and then you plug that in to have the multiplied equation. And then what you need to do is you make sure you multiply correctly in order to get the correct answer. Otherwise, you'd have a mistake from not multiplying correctly. So here you have to sum up. So these two, you sum these up, and then you multiply to each term here to get the correct answer, which would be 3.4d6. And so for each value here, s is 1.5. So you have to plug in 1.5 for each s here to erased by the different powers. And sigma is 0.1. And then you just solve that to get 3.46. And then next question asks to use the Bragg-Zimm model to calculate the partition function. So here, actually let me go back a bit. So here in red is another way to solve this problem for the zipper model. Either, depending on your exam, you may need to memorize this bottom one. Otherwise, you could just use the top one to derive it. This would give both 3.46 as well. So this one uses the Bragg-Zimm model to calculate the partition function. So you do the same thing, except this is a different equation for the Bragg-Zimm model. And this has an extra set of terms right here as well, which make up the middle of these terms here. And so once you solve this problem here, you have Q is equal to 3.46 for this portion plus 0.1 squared times 3 times 1.5 squared plus 2 times 1.5 cubed. So this part is this part here. And so once you solve this, the partition function is bigger, which is 3.59, slightly bigger than the one for the zipper model, which is 3.46. This is 3.59 for the Bragg-Zimm model, which could be simplified to BZ model. So that's the partition functions there. So the next question asks to calculate the average number of helical monomers, which is shown in brackets with n, in the polymer. So the fractional helicity is the average of n, the number of helical monomers in the polymer, over n. So to calculate that, what you need to do, n is basically 4 because it's given the number of units. And so we need to calculate the average of n. We need to have the average n, we need to find first the fraction of helicity. So to do that is first calculate fraction of helicity of h. And to do that, you need to say of h is equal to. Now to solve this problem, you need to use this formula. And I'm just going to plug in the numbers. So 1 over n, which is 4, times s over q, the partition function. And this is basically, you take the differential of that, which basically, if you solve that, it would be s over 4q times sigma multiplied by 4 plus 6s plus 6s squared plus 4s cubed. And then plug in the values to find the fraction of helicity, which is equal to 1.5, 0.1, 4 plus 6 times 1.5, plus 6 times 1.5 squared, plus 4 times 1.5 cubed. And it says all over 4q, which is nq. And the partition function we calculated was 3.46. That is for using the zipper model. So this one you calculate n for the zipper model. That's why I use this number here. And so you get f of h is equal to 0.4355. Now, to find f of h, let's bring that equation down. We have, actually when you're looking for the average of n. So let me fix that. So f of h, we already calculated that to be 0.4355. So I'm just going to plug in the numbers and solve for the average of n. And this is 4, and we're solving for average of n. So to figure that out, basically do a simple multiplication, then you get the number of helical monomers in the polymer to be 1.73. That's using the zipper model. Now, what difference do the extra terms in the Bragg-Zimm partition function make to the average number of helical units? N. So it's the same for the tetrameric polymer, and so we need to calculate N for the BZ model now and compare the difference of the extra terms. So we're going to do the same thing. First, we need to calculate the fraction of helicity. So here's the equation to solve for this value here, N. And we need to first calculate the fraction of helicity, which would be the same equation as above. F of h is equal to 1 over 4, which is, that's why it's tetrameric, n equals 4, times s over q, the partition function for the Bragg-Zimm model. And you take the differential of that, which is this basically s over 4q multiplied by sigma times 4 plus 6s plus 6s squared plus 4s cubed plus sigma squared times 6s plus 6s squared. This is all in a bracket. And once you solve that, q here is equal to 3.59 because that's the Bragg-Zimm model. You should get a fraction of helicity of 1.5 over 4 times 3.59 times 4 plus 0.225. Which should give you an overall answer of 0.441. So that's the fraction of helicity for the Bragg-Zimm model. But we want to find this term here. So to do that, we basically plug in the value 0.441 is equal to n over 4, the average n over 4. And solve that, you get 1.765. So if you notice, the Bragg-Zimm model has a slightly bigger average number of helical monomers compared to the zipper model.